Hi everyone, I'm Jeremie Marlhens from the lab of Heinz Koppel in TU Darmstadt. And this work is about how to build multistable gene network, taking inspiration from neural networks. And it was done on collaboration with Christian Kuba-Samanigo. So one first thing that is striking in development is multistability. For example, a mesenchymal stem cell can become either a neuron or a muscle cell, but there is nothing in between. It will eventually lead to one of these cells. And this property was quite interesting for synthetic biologists. And so in the early 2000s, there is the team of J.J. Collins that built this toggle switch in which you have two repressors inhibiting each other. And so it eventually leads to either repressor 1 or 2 being expressed. Multistability is the same idea, but with more possible states. And this multistability is observed already for some time. So here we have Waddington already in the 50s that see this multistability as an energy landscape. And so in which we would have a bead rolling down and that would eventually finish in one of those four states. This idea of energy landscape is not new to science. This is used by physics. And one model is the Hopfield network. So that was rewarded by the Nobel Prize this year, in which you also have an energy landscape and the state of the system will eventually arrive in the state of low energy. And so the Hopfield network, how does it work? So the network will memorize some given pattern. So here, for example, we have two patterns. And then, depending on the initial condition, it will eventually converge to one of these patterns. So here we start with a noisy pattern, and we arrive at one of the logo. It can work with differential equations. So this simple equation is the network. And where is the memory? The memory actually is in the connection matrix W. And so how to build this matrix? That the strong point, I think, of Hopfield network is that it's directly calculated from the patterns you want to remember. So here we have the outer product of the two patterns. And so compared to other neural networks where you need optimization, you would use some gradient descent. Here you have a formula and hop, you have your network. So we were wondering, can we build genetic networks that behave like Hopfield networks? So that would be very easy to design and that would eventually converge to one of our desired states. The problem is that the neurons of the Hopfield network are pushing each other toward positive or negative values. In biology, we don't have those. So what do? We use a reaction that is used more and more by synthetic biologists. So the sequestration reaction that can calculate a subtraction. So here we have 4 active X unit and 2 Y, and we have 4 minus 2. We end up with only 2 X units. So in that case, we have active depletion of the X. If we only rely on passive degradation, it won't be fast enough. So using this reaction, we will build one neuron. So one neuron is a pair of X and Y that sequestrate each other. And the second part, we have to build the interaction between neuron, so activation or inhibition. For activation, X will be the transcription factor. So if X neuron I activate neuron J, it means that the X will activate the transcription of each other. For inhibition, the X of one neuron can activate the Y of another neuron and triggering the sequestration of the corresponding X, and so depleting the other neuron of its X. So in that case, X is the positive values and Y can be the negative. And we can push toward +1 or -1, depending on who we activate. So after that, we did some simulation. So a simple one, we have here 3 neurons. The white value is the positive and the black is the negative. So Y, X is high and black, Y is high. And we can see that different simulations eventually converge if you let it long enough to the desired pattern. You can have also more complex circuits with more neurons and more patterns saved. And in that case, each simulation will eventually converge to pattern 1 or pattern 2. So that's great. We have some behavior that we want, but then we wanted to see how do they do compared to Hopfield network. So to do so, we compared the two simulations. So we have in dotted line the simulation of the Hopfield network, and in plain line the simulation of our molecular Hopfield network. We have a simple network with only 3 neurons and one patterned memory. And what we will do is increase the sequestration level to see how the simulations compare to each other. So by increasing the sequestration level, we realized that the molecular Hopfield actually converge. So its ODE solution converge exactly toward the solution of a Hopfield network. And it turned out that if we let this sequestration rate tend to infinity, we find that the ODE equations is actually the exact one from the continuous time Hopfield network. The difference is that in our case, we will have activation function that may be a bit different from what you usually have in Hopfield networks, but it has the important properties. So it's monotically increasing and it saturates in minus and plus infinity. Furthermore, if we allow more rules, so if we allow Y to be a transcription activator, in that case, we can also obtain a smooth activation function. So that's great because we have a lot of properties from the theory of Hopfield network that we may use to predict our molecular system. So for example, how many states can we have in memory for a given number of neurons? So for a given neuron, number of transcription factor, how many states can we have? Also the convergence properties. So depending on the initial state, where do we eventually end up? Now, we didn't build this in the lab, it's only a model. We may have some ideas on how to build it. So one could be in mammalian cells. So this is the work from the Elovitz group, where they use zinc fingers and leucine zippers that are easily programmable. Another one would be in E. coli, where we can use sigma and anti-sigma factors that also have this sequestration reaction. Finally, I want to come with some limits and also some ideas to further expand this work. So one is that the Hopfield network is fully connected. So each neuron is connected to each other, meaning that each transcription factor have to activate other one and also be activated. So it's not very obvious on how to do this. A second one is that the weight connections might not be symmetrical because, of course, the kinetic rates of different transcription factor and sequestration might be different, and this will affect also the solution of the Hopfield network. And finally, what we want to prove is if the sequestration rate is not infinity, can we still have the nice properties of Hopfield network? And I think this is the key takeaway from this talk is that in the case of our model, we have a very nice framework where the information is really encoded in the interactions between the different units, and that show this multistability. So here that's also shown by Waddington, where different genes interact each other to build where the cell will eventually be. So I would like to thank my professor, Hans Koppel, who gave me some feedback, and also the many ideas I got from Christian for this work, and also you for your attention. And I'll be open to questions. Thanks.